Today we study X20Q. You can download this PDF file after visiting the website kpop.org, and you will find the table of contents. This is X series, and then X20. The main textbook for X20, Newton's law of universal gravitation, is contained in X, and the corresponding lecture is available by clicking this. You will find the Korean version and English version as well. And there are checkpoints, many simple problems involving this subject. And then to attack the problems contained in X20Q, it's better to review X20NQ. Now we are ready to start X20Q. Newton's law of universal gravitation. After recording this lecture, it will be available at YouTube, our homepage, at YouTube homepage here. There are many playlists. Among them, you will find these X checkpoints and main text X and so on. Okay, let's begin with problem 1. We consider a two-body system consisting of two masses, m1 at x1, m2 at x2, in the center of mass frame. The center of mass of two-body system is defined in such a manner. Because we are at the center of mass frame, this center of mass is chosen as the origin of the coordinate system. The vector corresponding vector is zero vector. Because the denominator is non-vanishing, this one is equivalent to the fact that mass times position vector plus mass times position vector for two particles is 0. In Newtonian mechanics, mass is independent of time. Therefore, we can take the derivative and it does not affect the mass. As a result, first order derivative is 0, and the second order derivative is also 0. Perhaps you have noticed that fact, mass times velocity. This is the linear momentum of the first particle, and this is the linear momentum of the second particle. We shall find that this is the total linear momentum of the whole system at the center of mass frame, in which total mass multiplied by the center of mass velocity, this is the total linear momentum. This is the same as this. And this equation shows that the force, this is the force, net force applied to the particle 1, and this is the force, net force applied to particle 2. This sum of these two forces becomes 0. And actually, this is the net force applied to the whole system. And that is 0 because we are at the center of mass frame. We introduce another important vector. In addition to the center of mass, we have relative coordinate vector. Relative coordinate vector is R, defined by x1 subtracted by x2. That is the relative position vector of the first particle observed at the position of particle 2. All right, so let us recall this. So what's that? We Right now we neglect any external forces exerted on the system. So the only force applied to particle 1 is the interaction between particle 2. This is this. So this is the force applied by particle 2 to particle 1. So this one is equivalent to the mass times acceleration of the first particle. So in a similar manner, the acceleration multiplied by the mass of the second particle is the net force applied to the particle. That is the force applied by particle 1. As a result, we use this to find that the acceleration of the second particle is completely expressed as in terms of the acceleration of the first particle, and the ratio is determined by the masses. Why don't we take the second order derivative of this relative coordinate vector, that is the acceleration of the first particle subtracted by acceleration of the second particle. Because x2 double dot is completely determined by the x1 double dot, so we substitute this one in here to simplify the result as. Solving this system of linear equation, this is the definition of the center of mass, and we have a relative coordinate vector. Using these two relations, I can always express the x1 and x2 in terms of as a linear combination of xxm and the relative coordinate vector. You will find that this xm is common, and these two cancel, that disappears at the center of mass frame, at which the center mass is placed at the origin. In addition, we have a factor in the numerator multiplied to the relative coordinate vector r. This is the mass of the other particle. This is the mass of the other particle. In addition, they are opposite. They are opposite. We have center of mass, and particle 1 is somewhere around here, and particle 2 is there, and particle 1, particle 2, and the center of mass, they are all aligned on a single straight line. Because center of mass is between them, their directions from Cm to 1 and the Cm to 2, particle 2, they are opposite. This one represents this relation. And the mass of the other particle appears because, for example, if it is very heavy, the center of mass is near to the particle 2. So the distance from the center of mass to the lighter particle is longer than the distance from the center of mass to the heavier particle. Okay, that's the reason why the numerator contains the mass of the other particle instead of its own mass. Now we checked our computation by making use of this relation here. I can substitute x1 here, take the second order derivative, and simplify the result. In the end, you will find at the center of mass frame, this one vanishes, and this is trivial. They cancel exactly, and we can reproduce the second order derivative of the relative coordinate vector. You can check the calculation by making use of this mathematical code. Number 2, we consider an isolated two-body system consisting of mass m1 and m2. We are at the same situation. We'd like to compute the second time derivative acceleration of the relative coordinate vector. That is the acceleration of the particle 1 subtracted by acceleration of the particle 2. We know there is no external force applied to the system. The only force is the force applied by particle 2. The only force for particle 2 is the force applied by particle 1. As a result, in addition, we make use of the Newton's third law, that is the law of action and reaction. The magnitude of the two forces are the same, but their directions are opposite. So if we make use of this result, substitute this one, then this sign flips to become a positive sign. You will find the reciprocal of mass m and reciprocal mass 2 at their sum. We define this one by the reciprocal of the reduced mass that is called mu. If you combine these two terms into a single denominator, you will arrive that the sum is in the numerator and denominator contains the product. So if you flip the numerator denominator, reduced mass is expressed as the product divided by sum of the two masses of the particles. All right, because of this relation, I can express the force applied to particle 1 by particle 2 is the reduced mass multiplied by the acceleration of the relative coordinate vector, that is x1 minus x2, so second order derivative. We know the Newton's third law of motion states that this is opposite. They are opposite, so the magnitude is the same, only the sign differ. Okay, so this is the same, and I exchange the order to find to make a sign difference. In addition, why don't we find the magnitude of this? The magnitude of this is the magnitude of the relative acceleration of the relative coordinate vector. That is eventually expressed in terms of this. So this is reciprocal of the reduced mass. As a result, in addition, if the force is a central, usually we consider this central force, the force applied by two particles is always parallel to the line that connects the two particles. Therefore, the force, magnitude of the force can be projected by multiplying the relative coordinate vector. We make use of the acceleration because they are parallel. So relative acceleration is multiplied by the scalar product. And let's see, this is by definition relative coordinate vector's acceleration. And then we make use of this to find the square of this force divided by reduced mass. This relation reproduces the definition of the reduced mass. We apply this one to describe the motion of the two particles on the gravitational force. We have particle m1 and particle m2, and they interact with each other under the universal gravitational force. And capital G is the gravitational constant, and these two are masses, and this ER hat is the unit vector along the relative coordinate vector that is defined by the displacement of particle 1 relative to the particle 2. The unit vector along this and R is the magnitude of this relative coordinate vector. So we repeat the definition of the relative coordinate vector, and ER hat is the unit vector along that relative coordinate vector. And R is the magnitude of this relative coordinate vector, and mu is the reduced mass of this two-body system. We recall that the velocity of relative coordinate vector that can be described in terms of polar coordinate system in a two-dimensional Euclidean space. In that case, this r is because of this r vector is r multiplied by the unit vector along that direction. If I take the time derivative to find out the relative coordinate vectors of velocity, I have a radial velocity multiplied by the unit vector along the radial direction. And in two dimension, the differential of the displacement also has the component that is perpendicular to the radial direction. That is the tangential direction. And we remember that radial direction is described by, can be expressed as a linear combination of two unit vectors on the Euclidean plane using the Cartesian coordinates. So they are cosine sine, and a unit tangential vector is a perpendicular to the radial vector along the direction of angle counterclockwise. So it is a minus sine theta and cosine theta. All right, so this is the velocity. Discuss the orbital angular momentum of the system. The particle 1's position, particle 2's position can be expressed as a linear combination of the center mass and the relative coordinate vector as we already derived. Using this and at the center of mass frame, this guy disappears and x1 and x2 are greatly simplified as a vector that are opposite to each other. This relation holds for the velocity and acceleration as well. We copy this, so we multiply m1 in here, everywhere m1, then we find the product and sum and relative coordinate vector. The vector is, we know what it is, and this is the reduced mass. In a similar manner, we can multiply mass m2 to the position vector for the particle 2, that is this. Because of this negative sign, we have a negative sign, and they are exactly the same except for the sign. The relation holds even after taking the time derivative and reduce the mass multiplied by the velocity of the relative coordinate vector. We multiply these two by cross product, and mass squared appears in x1 cross x1 dot. We remember this is at the center of mass frame. It is completely expressed in terms of relative coordinate vector and its time derivative. We now know this is a plus and this is minus, this is plus and this is minus. Therefore, this product is the same for the other particle. So even though x or x dot are opposite for particle 1 and 2, their cross product, they are the same. They are exactly the same. All right, so we use this, and this is mu squared, and time derivative appears in here and relative coordinate vector, and we copy the result for the velocity of the relative coordinate vector, and we find this, and this is proportional to the radial direction. So radial direction cross product vanishes. The only contribution that survives is the tangential vector because ER cross E theta is E3. As a result, we find that mu squared R squared theta dot E3 hat is the cross product of these two objects. Next, we compute the total angular momentum of the system. The total angular momentum, and actually this orbital angular momentum. In classical mechanics, the angular momentum is the only one that represents the angular momentum, that is a orbital angular momentum. But in quantum mechanics, there is a new angular momentum appears that is completely independent of the orbital angular momentum. So it doesn't require an of the motion of the center of mass, and it does not require the structure in it. So that is a spin angular momentum. However, in classical mechanics, so we are fine with staying in this concept of orbital angular momentum only. Anyway, position vector cross product with its linear momentum is the orbital angular momentum of the first particle, and the other one is the orbital angular momentum of the other particle. The sum of them is the total orbital angular momentum of the two-body system. Okay, so we are ready to simplify this with previous results. They are mu squared r cross r dot. Okay, so if I make use of these relations, I finally find that we had this result when we multiplied masses squared, but here we require only a single power, so we have to, if we make use of this result, then we have to divide them by 1 over mass. So 1 over mass of a first particle, 1 of the mass of the second particle is additionally multiplied. By the way, that what is that? This is a 1 over reduced mass that cancels the power of the single power of the mu squared in here. Finally, total orbital angular momentum of this two-body system is completely determined as reduced mass and relative coordinate vector squared and theta dot. And the direction of the orbital angular momentum is perpendicular to the plane on which the two particles' motion is restricted to. Okay, so we are familiar with the r squared theta dot because the sector of a circle with angle d theta and radius, then what is the differential of this area? 1/2 r squared d theta. This is the differential area element of a sector of a circle of radius r with angle d theta. Or why don't we take the time derivative of this area? This is called 1/2 r squared theta dot. Okay, 1/2 r squared theta dot is completely expressed in terms of the orbital angular momentum's scalar product with E3 hat divided by 2 times the reduced mass. And this is nothing but the aerial velocity. The area, this area swiped by the orbit per unit time is called the aerial velocity. And this aerial velocity is conserved because the total angular momentum of a two-body system that are being communicated with each other or via a central force is always conserved. So this time derivative is a zero. So it is a completely constant. That is called Newton's second law. Next, we consider Newton's first law, that is the that states that for two-body system under gravitational force, if the total mechanical energy is a negative, then its orbit is an ellipse. And the circle is a special case of an ellipse. Okay, why don't we consider the fact that the gravitational force is a conservative force? If the force is conservative, then our total mechanical energy, that is the sum of the kinetic energy and the potential energy, is always conserved. Conserved means its a time derivative is zero. So it's a total mechanical energy is a constant motion that doesn't change at all as time goes by. We define effective potential energy. First of all, we have a gravitational potential energy that disappears as r goes to infinity. Well, because uh, it is allowed, we are free to choose any constant added to the potential energy, but the simplest choice is to take the potential energy to be zero as r goes to infinity. Okay, by the way, the total mechanical energy is the sum of the potential energy written this like this and the kinetic energy that is 1/2 mu r vector squared. And this r vector is velocity is r e to the r plus r theta dot e theta. And we know they are perpendicular to each other. Therefore, the kinetic energy can be expressed in terms of 1/2 mu, that is the reduced mass r dot squared, plus r squared the theta dot squared. And we make use of this term. This we call it as a radial r dot is a radial velocity, and this tangential velocity and velocity squared. And because we know the orbital angular momentum, total orbital angular momentum of this two-body system is conserved, so we can replace this one. R theta dot is the tangential velocity, that is L over mu r. And this, they are equivalent. So theta dot can always be expressed in terms of orbital angular momentum and radius. So we substitute this one here, that we have this term, this kinetic energy is expressed as a 1/2 mu and L over mu r squared. You will find you have 2 times mu times r squared L squared. Okay. This is indeed depending on the radius, and it behaves like a potential energy. If you integrate out this, we remove this theta dot contribution in terms of radius. Therefore, we can decompose this two-body system happening in the two-dimensional Euclidean space, and just like one that appears in one dimension, that is along the radial direction only. So we just find out the projection onto the radial direction, and this theta dependence is completely replaced with r dependent term. Therefore, we say this effective one, that is kinetic energy, radial kinetic energy. And the remaining piece, that is the sum of the gravitational potential energy and the rotational kinetic energy, this one to be the effective potential energy. If we ignore this, the gravitational potential energy decays to the minus infinity as r goes to zero. However, we have orbital angular momentum squared positive value, and we have the denominator r squared in the denominator. This term wins the game against the gravitational potential energy as r goes to zero. It is a much bigger, and as r goes to zero, this one, the sum of this, will blow up. Instead of going into the minus infinity, this one makes the effective potential energy to be plus infinity as r goes to zero. So you will find that effective potential energy is this kind of shape, and this is the direction of radius r. Okay, that's the reason why we have a bound state whose total mechanical energy is negative has two solutions that are called R maximum and R minimum. At a certain point at which its potential, effective potential has the derivative vanishing, this is the only single radius allowed. That means alpha. That is the radius of a circular orbit. Okay, so now we would like to determine what these ranges of the radius allowed by this Newton's gravitational force. We remember this is this effective potential energy determines the total mechanical energy. And in here, aha, these are turning points. And if energy is low enough and we have a radius only, and this is the only allowed radius. If you look at the conservation of the total mechanical energy and just to simplify our problem, we ignore this at which this is allowed at the turning points. At turning points, radiokinetic energy vanishes. And if energy is low enough to arrive at a circular orbit, again, R dot vanishes too. So we would like to find these two or these by making use of the total mechanical energy conservation relation. That is this at the turning points. You must have found that this total mechanical energy's absolute value is a constant. Everything is constant except for the radius. And you will find this is the quadratic equation of 1 over r. And for simplicity, we define u by the reciprocal of the radius, the magnitude of the relative coordinate vector r. And middle school student can solve the quadratic equation, and you find the case at which this quadratic equation has a single solution, and that is double root. The double root appears when the discriminant of a quadratic equation becomes zero. So that constraint is that 1 over r, that is u, is 1 over alpha, and we call this alpha the radius of the circular orbit to be semi-latus rectum. Semi-latus rectum. Okay, that is completely determined by the gravitational constant and mass and orbital angular momentum of the two-body system. Okay, if we increase the energy, then there will be two solutions of the quadratic equation, and the two quadratic equations solutions can be obtained by a simple form, some x squared minus a squared equals 0, something like that. Then it will give plus minus a, two solutions. This one determines the value of u, and there's a detail how to determine this. You will find this guy completing the square subtracted by a constant. This constant is identified with a number in the range between 0 and 1. We call it eccentricity. If this eccentricity becomes a 0, then the solution is a double root that is a circular orbit. If it is not the case, we have two solutions, and that determines the minimum and maximum radius. And we have a special name for this historically. Okay, that's it for today. Thank you.